function here in this section and introduce a new aspect of our graphing rational functions, specifically finding holes. We've talked about the different types of discontinuities, and one of those types of discontinuities are these kind here, which we've been calling removable or point discontinuities. They can also be called a hole. So when do those occur? Well, when a rational function has a duplicated factor in both the numerator and the denominator. That's the key. If you see the same factor in the numerator and the denominator, the function will have a removable or point discontinuity. We can also call that a hole corresponding to that factor. For example, if x plus 3 is a repeating factor in both the numerator and the denominator, then there will be a hole at x equals negative 3. Okay, so if you were to set that factor equal to 0, that will tell you where the hole is. Okay, a little bit weird here at first, but let's go ahead and do an example and hopefully we'll feel pretty comfortable. So we're going to graph this function here, h of x, which is 3x plus 6 over x squared minus 4. And we know that to graph a rational function, we want to find intercepts and asymptotes. So our x-intercept corresponds to when we set the function equal to 0. But really, the only way a fraction is equal to 0 is if the numerator is equal to 0. So we really just have to set the numerator equal to 0. If we solve for x here, we'll get x equals negative 2 is our x-intercept. Our y-intercept we can get by plugging 0 in for x. So we'd have 3 times 0 plus 6 over 0 squared minus 4 is 6 over negative 4, which is negative 3 halves. So we have a y-intercept at negative 3 halves. Onto our asymptotes. The vertical asymptotes are found by setting the denominator equal to 0. And we'll notice the factors here are x plus 2 times x minus 2. And this might be a tricky thing to recognize here. But if we were to take that numerator, we had 3x plus 6, and we set it equal to 0, right? Well, really, there's a common factor of 3, and we could have factored that out to be x plus 2. And when we set x plus 2 equals 0, we'll still get x equals negative 2. That is still our x-intercept. But we'll notice here that I have a repeating factor in the numerator and in the denominator. And this is the case where I have a hole. Okay, so right here, x plus 2, these two factors repeating tell us that there will be a hole at x equals negative 2. Now this is a bit of a strange thing, because what that means is if there's a hole there, the function value actually doesn't exist there. So this is kind of a weird thing here. X equals negative 2, our x-intercept is actually going to be a hole. And we would have had a vertical asymptote at x equals negative 2, but there's no vertical asymptote there because it's a hole. So the hole kind of trumps the other things. If you see this repeating factor, then that is a hole in the graph, and we'll see what that looks like in a minute when we get through the rest of it here. Continuing on with vertical asymptotes, we would have a vertical asymptote at x equals 2, but not at x equals negative 2, because that's a hole. And then we can find our horizontal asymptote by comparing the degree of the numerator to the degree of the denominator. The degree of the numerator is 1. The degree of the denominator is 2. 1, of course, is less than 2, so n is less than m. When the degree of the numerator is less than the degree of the denominator, that means our horizontal asymptote is y equals 0. That was in our rules from the last section, or the first part of this section. So we have vertical asymptote at x equals 2 and a horizontal asymptote at y equals 0. We can go ahead and start graphing this. We're going to graph our asymptotes first. X equals 2 is our vertical asymptote. y equals 0 is our horizontal asymptote. And now it's a little bit strange here. But my x-intercept was going to be at -2, but we don't have an x-intercept there. We actually have a hole there. Okay, so we're not going to put anything, we're not going to graph anything there yet. We do have a y-intercept though at -3/2. So -3/2 is right there. Let me switch to blue to draw the actual graph. So I've got my y-intercept drawn, and now it's a little bit weird here because I'm not sure what else I'm going to need to graph. So at this point, I'm probably going to want to plug in some extra points and see what's going on. All right, so although we can plot more points if we want to, or if you're feeling like, oh, well, there's a point here, it has to be bounded by these asymptotes, then you could go ahead and draw that curve in there, and we would be good to go. And then follow our sort of guideline that we've said that if it's going down on one side of the asymptote, it has to be going up on the other side of the asymptote. And that would work out well in this case. If you want to have a little more assurance, let's go ahead and find some function values. It's nice in this case that x equals 1 will be an easy function value for us to figure out. So, sorry, at h of 1, not f of 1. H of 1 would be 3 times 1 plus 6 over 1 squared minus 4. That's going to be 9 over -3, which is -3. So we know at 1, our function value is -3. And that gives us a good sense that, yeah, as we come to the right, this is going to go downward, bounded by that asymptote. And as we come to the left, it has to approach that horizontal asymptote. So we would have this expression, or this curve right here. And again, it's not a universal rule, but it's essentially a rule that as you look at the vertical asymptotes, the function has to go in opposite directions. But again, if you want to make absolutely sure, we could plug in h at 3. 3 is right here. All we need to know is whether it's positive or negative. If it's positive, it's above the asymptote. If it's negative, it's below. So we'd have 3 times 3 is 9 plus 6 over 3 squared minus 4. So this is going to be 15 over 5, which is positive 3. And so we have at x equals 3, our function value is positive 3. And we can again see that the asymptotes are going to force the function to go up toward infinity as x moves to 3 from the right, and move closer and closer to 0 as x goes up toward infinity. So we're bounded in this top right corner by the asymptotes. Okay. Now, the last thing here that I kind of forgot about, or didn't include in our graph so far, is that we have this hole. So don't forget about this hole. There is a hole at x equals -2. So at -2, we need to indicate that hole on our graph. So we can't just draw a solid curve through there. We have to put that hole at -2. We see where the curve's heading, so we'll put the hole right where it would go if the curve were smooth and continuous. Oops, I accidentally deleted the whole curve. Okay, so here's our curve. It goes right up to the hole, and then there's a gap, and then it keeps going out toward the horizontal asymptote as we move left. Okay, so make sure you indicate the hole visually if you do draw a graph with a hole in it. That's a key feature of it. It's important to recognize it. If you were to draw on a graphing calculator or using Desmos or whatever, you actually won't be able to see that hole because it really is infinitely small. But if you were to sort of hover, like at least in Desmos, if you were to hover over it, it would show you that it's undefined at that value. Okay, so that's graphing rational functions. I would encourage you to use a calculator or Desmos to check your work. Don't just copy over pictures of them, though, when you're doing your homework. You really need to get into it and do these out by hand and show all of your work when you're graphing a rational function. I need to see all of this work for me to feel confident that you knew what you were doing and weren't just copying off a calculator screen. So show me how to find the intercepts and the asymptotes as a way of showing your work on the homework. I should see all of that work. And we're going to practice that on the homework tonight, and then a little bit more or whenever you do the homework from this particular section. And then the next section is just going to be one more little twist and just more and more practice of graphing a lot of different rational functions. So make sure you're practicing it, doing all the steps out by hand. But here are some problems to start practicing on those skills that we've learned so far. Notice it's just drawing 4 rational functions. We'll get plenty more practice though as we go through the week.